Welcome to this lecture on insect vectors and diseases. Today, we are going to explore a fascinating and highly relevant topic, bedbugs as mechanical vectors. While mosquitoes and ticks are famous for incubating and spreading deadly diseases, bedbugs operate quite differently. We will uncover how these common household pests can act as microscopic delivery vehicles for pathogens, and why this matters for public health. To begin our journey, let us first understand what we mean by mechanical transmission. Think of a delivery truck that picks up a package from one house and drops it off at another. The truck driver does not open the package, change it, or make copies of it. They simply move it from point A to point B. In the world of diseases, some insects act exactly like this delivery truck. A mechanical vector is an organism that transmits a pathogen from one host to another without the pathogen undergoing any biological development or multiplication within the vector's body. They act like dirty needles. Now that we understand the delivery truck analogy, let us look at our specific vector, the bedbug. Scientifically known as Cimex lectularius, these are blood-sucking insects that feed primarily on humans. While they are notorious for causing psychological distress and itchy allergic reactions, their role as mechanical vectors is what we are focusing on today. Because they feed on blood, they can theoretically harbor pathogens on their piercing mouth parts, on their legs, or even in their feces. If a bedbug feeds on a person with a high level of bacteria in their blood, those surviving bacteria can be physically rubbed or injected into a new host. This mechanism of transferring bacteria brings us to a very important question. Why do we care if bedbugs do not cause massive plagues? The reality is that in highly crowded or unsanitary environments, such as homeless shelters or densely packed apartment buildings, the risk becomes a serious public health concern. Bedbugs have been found carrying dangerous, drug-resistant bacteria, like MRSA, on their bodies and in their digestive tracts. When a person scratches an itchy bedbug bite, they create an open wound. If the bug has left contaminated feces nearby, the person can easily rub the resilient hospital-grade bacteria directly into their own bloodstream. To truly understand why this mechanical transmission is relatively rare but still possible, we can model it mathematically. The overall chance of a successful transmission event depends on three distinct independent steps that must all occur in sequence. This gives us the formula PT equals PP times PS times PD. Here, PT represents the total probability of successful mechanical transmission. PP is the probability that the bedbug successfully picks up the pathogen while feeding. PS represents the probability that the pathogen survives on the outside of the bug during its journey. Finally, PD is the probability that the bug successfully delivers the surviving pathogen into the new host. If any of these individual probabilities decrease, the overall chance of transmission drops significantly. Before we move on, let us see this formula in action with a concrete example. Imagine a bedbug feeds on a host infected with a skin bacterium. Research shows there is a 40% chance the bug picks up the bacteria, so PP is 0.40. Once on the bug, the bacteria has a 25% chance of surviving the journey, making PS 0.25. Finally, there is a 10% chance it is successfully delivered, so PD is 0.10. We multiply these decimal probabilities together, 0.40 times 0.25 times 0.10. This gives us 0.01, or exactly 1%. This low probability perfectly explains why bedbugs are not major drivers of epidemics. That 1% probability we just calculated relies heavily on the pathogen surviving the journey. This brings us to a crucial biological reality. Pathogens generally do not do well outside of a host. When bacteria or viruses are exposed to room air on a bedbug's mouthpart, their population decreases exponentially over time. They dry out, starve, or are destroyed by environmental factors. Therefore, time is the absolute enemy of mechanical transmission. The longer a bedbug wanders around the bed sheets before finding its next victim, the fewer viable pathogens it carries. This rapid die-off is the main reason why mechanical transmission by bedbugs remains relatively rare. To quantify this rapid die-off, we use a mathematical model for exponential decay. The formula is n of t equals n0 times e to the power of negative kt. Let us break down what each symbol means. N of t represents the number of surviving viral particles at any given time, t. N0 is the initial load of viral particles the bedbug picked up from the first host. The variable k is the decay constant, which tells us how quickly this specific virus dies in room air. Finally, t is the time elapsed in hours. As time t increases, the negative exponent grows larger, which physically means the number of surviving pathogens drops rapidly toward zero. Now that we have our decay formula, let us apply it to a real scenario. Suppose a bedbug picks up an initial load of 1,000 viral particles, so N0 is 1,000. The decay constant, K, for this virus is 0.693 per hour. We want to know how many particles survive after 2 hours, so T equals 2. First, we multiply the constant and the time in the exponent, giving us negative 1.386. Evaluating e to the power of negative 1.386 gives us approximately 0.25. This means only 25% of the virus survives. Multiplying 1,000 by 0.25 gives us a final answer of 250 viable particles. In just 2 hours, most of the threat has naturally neutralized. Having calculated the math behind the pathogen's survival, let us visualize this entire journey. On the screen, you see a clear schematic of the mechanical transmission cycle. On the far left, we have the infected host. The bedbug feeds here, picking up the pathogen, represented by the red dots, onto its mouthparts. The middle section shows the bug traversing the white bedsheet. Notice how some of the red dots are lost during this transit. This visually represents the exponential decay and pathogen die-off we just calculated. Finally, on the right, the bug reaches the susceptible host. It pierces the skin, and the surviving red dots are mechanically transferred into the new host, completing the transmission cycle. This visual journey brings us to a critical realization about public health. While the mathematical probability of this transmission is generally low due to the rapid pathogen die-off we discussed, the sheer number of bedbugs in an infestation changes the game. In crowded environments, secondary infections like MRSA can spread rapidly through contaminated bedbug feces and scratched bite wounds. The pathogens simply hitch a ride on the bug's exterior or in its digestive tract to be excreted later. Understanding this mechanical mechanism empowers us to see pest control not just as a way to get a good night's sleep, but as a vital form of disease prevention. We have covered a lot of ground today, so let us review our key takeaways. First, bedbugs act as mechanical vectors, functioning much like contaminated needles that physically transfer pathogens without the germs multiplying inside them. Second, we learned that the overall chance of transmission is a product of the pickup, survival, and delivery probabilities. Third, time is the enemy of the pathogen, as their survival on the bug decreases exponentially the longer the bug wanders. Finally, despite the low individual probability, the risk of spreading resilient bacteria like MRSA makes bedbug control a critical public health priority. Thank you for joining this lecture, and you now have a solid understanding of mechanical transmission.